So you might have heard of the game Xcom or something. I don't know if you ever played that game, but I was doing some research on center of mass, center, center of mass. That would be Xcom. Uh, and I was getting a whole bunch of results for some video game, maybe in 1994 or something. Okay, well, Xcom is simply the center of mass, the position of the mass, where all the mass is centered at. So let's say, first I'll write out the equation. So we got a capital R, capital M, capital R. This is mass, and this is the radius of where that center of mass would be, plus a smaller mass perhaps, and another radius of where that center of mass would be. I'm going to draw a line under it that's actually going to be divided by the m plus m. So this is the big M and the little m. So the sum of the total masses at the bottom, and then we've got the basically individual masses, where they are, the position of where they are along a certain radius from a center. Now you need to set up a coordinate system for this. So I'm just going to sort of do that kind of along the equation. Just an equation with a visual diagram on top of it. Interesting. We're going to call this the origin right here. So the radius is actually along the x-axis over here. This is the x-axis, right? Let's just say this was 6 meters long, okay? And this is the plank, let's say a plank of wood, and we're going to try to calculate the center of mass of this plank of wood. Usually the center of mass would be right over here for the plank of wood. This would be the center of mass, and it should be, let's say, 1 kilogram. Okay, and this would be at the 3 meter point because that's right in the middle. Okay, that's usually where you'd have, let's say, a plank of wood. All the mass has been concentrated 1 kilogram right here into the center. That's the center of mass of a plank of wood. All right, it's 6 meters long, 3 meters right there in the middle. Now let's just say you also had a weight right here, this big weight, and let's say that weight was at 1 meter. And the weight was, say, 5 kilograms. 5 kilograms. All right, so it's a pretty heavy weight that we stuck right there on this plank. And over here on the other side, say around 5 meters, we stuck another weight. I guess we'll make this 2 kilograms. Okay. So there's another weight over there that's 2 kilograms. Got the plank of wood that's 1 kilogram, and another mass over here that's 5 kilograms. And we're going to try to figure out what is the center of mass of this whole object. Kind of cool how we did it on top of our equation, but it's, yeah, and we made sure that this was the origin here. All right. Now let's say this was along the y-axis. Obviously, you would simply do the same thing, but with the y-axis directions over here for the r-com. This is why I kind of called it r-com instead of x-com, because this is x-com, this is the center of mass in the x direction, and we're just using the particular radiuses of this. So this is radius right here, and this is the radius right there. So let's kind of finish this off. I suppose what we would have is something like this. We would get that Xcom is equal to the first mass, which is 5 kilograms. 5 kilograms times 1 meters, M times R. That's just 5 kilogram meter. All right, and then over here we've got the next mass. That's going to actually be the weight of the plank itself, right there at 3 kilogram times 1 meter, or 1 kilogram times 3 meters gives us 3 kilogram meters. And then we're going to add the next mass, and this keeps, by the way, this could be any number of masses at the top here. So it's mass number 1, mass number 2, mass number 3, could be mass number 4, 5, 6, could keep going. Put some dots right there. At the bottom, you're just, again, adding up all the masses that you included in this equation. So over here, this is going to be mass number 3, and that's this little ball. Mass number 1, mass number 2, and mass number 3 is this little ball right here. That would be 5 times 2, so 10 kg meters. Okay, everything should be relatively simple so far. And we're just going to divide this by, well, mass number 1, mass number 2, mass number 3. This is only the masses now, so there's no longer going to be a meter next to it. Okay, now it's just the masses. The first mass was 5 kilograms, and then we had 1 kilogram there, and then we had another 2 kilograms over there. So, in the end, we essentially get this little calculation here. You're going to notice that the kgs will cancel, and you're going to be left with some sort of meter, and that is exactly where the Xcom would be. I guess it would be 18 divided by 8. So 18 divided by 8, that is the particular position of the center of mass of that object. Great. There's something else we can do with this sort of center of mass situation. We can also consider Vcom. And Vcom at first seems to be a little bit strange, but all it is the sum of the momentums divided by the sum of the masses. All right? And we can sort of represent that by saying m1v1 plus m2v2 divided by m1 plus m2. That's really similar to what we did up there, except instead of having the position being here, we're using velocity instead. Okay, so let's say we wanted to describe this in some sort of a diagram here. I'm going to use a train. All right, got a little train here. I'm going to give it 3 compartments. 1, 2, and here's another piece of the train. Alright, there's the train. And now, we got this runner. He's going to start over here on the train. And he's going to be trying to run as fast as he can to the other side of the train over here. Alright. So, let's just say he does that with some sort of a speed. Alright, we'll give him a blue little speed over here. He's going to be running at this particular speed. Let's say it's kind of like he's 10 kilograms moving at 10 meters per second. Let's see. 10 meters per second, and he is 10 kilograms. So he's going to be moving sort of like at 100, kg meters per second, right? That's going to be his momentum, the runner right there. Now this is sort of the right side over here. Keeping in mind that his center of mass is going to be right there where his body is, all right? And over here, the runner's center of mass is going to be right there where his body is. Again, he's still going to be moving at the same speed, 100 kilogram meters per second, with the same size arrow over here, 10 kilogram and 10 meters per second, all right? So this is the runner that's going to run from this side of the train all the way to the other side of the train. Just setting up our little example here. The train itself is going to be moving, here's its center of mass, right here in the middle of the whole train. And it's going to be moving pretty dang fast. I'll give it, this arrow. Let's make it slightly smaller on this arrow here, just so that we have some room for later. So we got an arrow here. It's traveling at this speed right here, all right? Bit more than the runner. All right, so let's say that was 100 meters per second and 100 kilograms. That means that the train will be running at, 10,000 kilograms meters per second. That's pretty fast. And so we have the train moving at that speed, and we have the runner moving at that speed, and so we're going to ask ourselves, okay, well, it's the center of mass of this object is technically going to change, because in this scenario, the center of mass of the object is here. Well, not really there. It's more closer to there. But it's essentially the center of mass of the object is somewhere around over here, right? On this side, because the weight of this runner is pulling down over here. So therefore, the weight of this object is more towards that side. Once the object is shifted over here, the weight of the object is going to be more on this side. All right? And so we're going to be asking ourselves, okay, well, how fast did it take the weight to shift itself to this side? What was the speed that the center of mass of this object shifted itself to that side? That's the way that we can kind of combine objects together, is we sort of think about, okay, well, the center of mass of all that stuff was over here, and the center of mass shifted itself over time because of the movement of all the other items over here. It's kind of weird how we can think about this. But in any case, this is now the Vcom. And that's what we got with this equation. So let's try to rewrite this for our example. We have Vcom at any one of these particular situations is going to be equal to the velocity of the train plus the velocity of the runner at any point. So that's kind of cool. And let's just rewrite this over here again with actual math. So we could say that mt, the mass of the train, times the velocity of the train, plus plus the mass of the runner times the velocity of the runner. And we're going to divide that by the mass of the train plus the mass of the runner. All right, and there we go. This is how we can figure out what Vcom is. So now we have Xcom and we have Vcom. Hopefully this wasn't too difficult to understand. If we were to consider how fast the Vcom was moving, it would actually be a bit larger. It would be the largest arrow that you have up here at the top. That's because we are actually adding all the momentums together. So you're going to notice that it's larger than the speed of the train because you're adding in a smaller momentum over here, but it's going to be faster than the speed of the train. So the Vcom in total is going to be the largest quantity out of any one of these individual parts. Now let's move on to another concept called inertia. Well, inertia. I guess we'll just go ahead and say inertia. Well, I'm going to write down the parallel axis theory of inertia because I feel like it's pretty important. This has to do with the length from the axis, or rather the distance from the axis. This right here is a parallel axis theorem, and it has something to do with inertia. Inertia. What is inertia? Inertia is essentially the resistance to movement. We have mass, and it's similar to mass. Inertia and mass are very similar. Inertia is very similar to mass. And resistance to movement means, on this side, the mass, I'm going to write this in red, mass is the resistance to move, generally going to be on the, this direction, just on a directional basis. Whereas the inertia, especially rotational inertia, is going to be resistance to, spin. All right, so something's spinning this direction, it's going to have an inertia, it's a rotational inertia, so resistance to spin and the resistance to move. That's going to be the difference between inertia and mass. So this parallel axis theorem is going to help us calculate the inertia of whatever particular object that we're going to be looking at. Let's say we have a strange object that looks something like this. Kind of like, I don't know, it's like this pendulum thing. And it comes down here, and it has a weight at the bottom here. And this pendulum is going to shift up here to this side at some point. Twist it and move it over here. Okay? This length is going to be the same, obviously, from here to here. These are the same length. But this center of mass right here, when it gets rotated up to this point, it's going to move up a certain particular, I'll put this part in blue. It's going to move up a particular height right here. This is going to be h, all right, from the ground. See, right here, this is the ground. So this mass is going to move up and rotate at a particular height up above the ground. But it turns out that if we go up here maybe halfway through, and we draw another parallel line here, this center of mass right here is going to move up about this way. And this distance from here to there is, from here to there, is actually half the distance, h over 2, from here to there. All right, that's because over here, this was done at the halfway point, so L over 2. This is L over 2. We'll move this center of mass in the middle of the pendulum up over here. And this side over here is simply the full length of this pendulum. So when it moves up here, this gets shifted. No, this is probably getting a little bit complicated and confusing, but let's just keep going. Let's say we had another piece right here. This will all make a little bit more sense in the end. As we start to twist this up, it also moves only a smaller amount. And let's say this center of mass was at L over 4. Well, that means that this, you guessed it, only moves up h divided by 4. Okay, so how does this help us? Well, this is just in case you have some situations where you might be having to set up potential energy over here, potential energy, and then you want to know the potential energy here or the potential energy here. You need to know what the heights are of these, and it's important to know that the center of mass is actually what's moving that space, that distance. All right, this may help in certain situations. We're going to calculate right now what the center of mass, well, not the center of mass, but rather the center of inertia is of this particular thing. This is a rod, right? So the inertia of a rod is usually going to be 1 over 12 ml squared. And this can be found from your inertia cheat sheet. Everybody should have an inertia cheat sheet where you have all the different inertias. And you don't want to use, this is important, don't use 1/3 for the parallel axis theorem. Don't use the 1/3 for the parallel axis theorem. If you're going to start using the parallel axis theorem to start shifting around the inertia of a rod, make sure to use 1/12. So if you put this into an equation, what we would get is that the inertia of this particular rod is going to be equal to 1/12 ml squared. That's the Xcom of the original, this is just the Xcom, original inertia, the original inertia of this rod. And then you're going to start adding in whatever you need to start messing with. So here is going to be md squared. If we were to translate that into md squared, then that would be plus the whatever mass that thing is, and then the length of the whole thing squared. So the total inertia of this particular rod would just be 1 and, well, I guess we could say 13 over 12 ml squared. It's just adding the initial original inertia with this little ball here. You could add that little ball and that little ball if you wanted to. It would just simply be L over 4, L over 2, and you just have to add that all in. So this is how you can use the parallel axis theorem to start adding together little pieces of items onto another item, similar to what we would do here with the Xcom, the Vcom, and technically Icom over here. That's how you can get the inertia of an item. This little section over here with the heights being lifted, that's just sort of, it's a nice little thing to have along with this, so you can sort of visualize this stuff a little bit better. So these little math tricks that you can, that sometimes they help you to solve these problems. It's nice to add that in along the way. So as you can see, understanding center of mass is helpful to be able to make the physics equations problems a lot more complicated because now we can start adding in multiple objects and stuff. So that's kind of cool. And we can also take a look at torque and other things like that, and rolling, etc., etc. So that's what's coming up next. Hopefully you enjoyed this video, and if you do, make sure to like and subscribe, and ask any questions you have in the comments so that we can all learn. Thanks for watching.